Hello, and welcome to this presentation, Understanding VHF Propagation. This presentation provides an introduction to both common and uncommon propagation modes encountered at VHF. This presentation consists of three parts. The first is a general overview of VHF, what it's commonly used for, and why we should study VHF propagation. The next section discusses the most common modes of propagation at VHF. These are the modes that carry VHF signals under normal circumstances. The third and final section provides an introduction to some of the less common VHF propagation modes and explains how even these less common modes are still important in many applications. The standard or nominal definition of VHF is from 30 to 300 MHz, but as a practical matter, VHF propagation modes often apply to signals up to several hundred megahertz or even a gigahertz. As we'll see in this presentation, propagation can, however, vary substantially, even within the more limited traditional VHF frequency range. VHF is very commonly used in many applications. Radio and television broadcasting are, of course, widely known, and most non-cellular local two-way voice communications are based on VHF. VHF can also be used for transferring data, particularly telemetry or other measurement data. Some of the navigational aids used in aviation, such as VOR and ILS, also operate at VHF frequencies. And finally, there are several types of radar that use VHF, such as the newer anti-stealth radars that use longer VHF wavelengths to minimize the effectiveness of stealth technology. Propagation at VHF is usually quite different from propagation at HF, so it might be helpful to start by talking about some of these differences. One advantage of VHF over HF is that antennas are physically smaller due to the shorter wavelengths. This makes VHF more suitable for mobile or portable use, either with handheld radios or on platforms such as vehicles, ships, and aircraft. VHF also enables much wider bandwidths to be used, and this in turn increases the data rates on VHF compared to the more bandwidth-limited HF. There's lower atmospheric noise at VHF versus HF, but man-made noise sources are often more common at VHF. VHF penetrates buildings better than HF, which is one of the reasons why VHF is so widely used in broadcasting. One potential problem area for VHF is a higher probability of multipath. We'll come back to this topic later in the presentation. All things considered, HF is usually best for longer distance communications. Global coverage is possible under the right conditions. VHF, on the other hand, is better suited for local applications, typically within a radius of roughly 100 kilometers or less. Why is it important to study propagation at VHF? As with other frequency ranges, application or mission planning requires knowledge of how signals propagate so that the necessary coverage and reliability can be achieved. This knowledge can be used to select the equipment, antennas, power levels, etc., necessary to meet requirements. There's also a very common misconception that VHF propagation is essentially just line of sight, and in this presentation, we'll show why this assumption is usually incorrect. There's a wide variety of different VHF propagation modes, and these are generally much more dependent on the local environment than HF propagation modes. And even beyond these various normal modes of VHF propagation, there are also several different uncommon propagation modes that can lead to VHF signals propagating much longer distances than expected. These uncommon modes can have significant implications with regards to radio frequency interference, direction finding, signals intelligence, etc. Let's start by discussing line of sight. True or pure line of sight is actually very uncommon in terrestrial environments, especially at distances of several kilometers or more. This is because signals usually encounter objects along the path between a transmitter and a receiver. Depending on the shape, orientation, composition, and other properties of these objects, the signal's direction, amplitude, phase, and/or polarization may be changed when a signal interacts with them. The longer the path, the more obstacles the signal encounters, and the greater the effects of these interactions. As we'll discuss in just a few moments, even in an object-free environment, the distances achievable using pure line-of-sight propagation would be limited by the curvature of the Earth as well. So how do VHF signals propagate in a non-pure line-of-sight environment? In this presentation, we'll cover the four most important common VHF propagation modes: refraction, reflection, diffraction, and scattering. These are in rough order of importance. Refraction arises from interactions with the troposphere, that is, with air, while reflection, diffraction, and scattering are caused by interactions with solid objects. The size, density, number, arrangement, and other properties of the encountered objects is what determines which of these three modes is dominant. The most important of these common VHF propagation modes is refraction. Refraction is a change or bend in the direction of a wave caused by different propagation velocities in different media. The direction of the bend and the amount of bending depend on the difference in refractivity between these two media. Waves are bent towards the region with higher refractivity. The amount of bending depends on the boundary between the two media. When the boundaries are gradual, as in this example, the bending is also gradual. On the other hand, more distinct boundaries, as shown here, cause much sharper refraction. The amount of refractivity of a medium is quantified using something called the refractive index. The refractive index, abbreviated N, represents the bending power of a medium. For VHF signals in terrestrial applications, the medium is the atmosphere, or more specifically the troposphere, which is the lowest layer of the atmosphere and where most weather occurs. For the most part, tropospheric refraction is independent of frequency, and this is different from ionospheric refraction, which often has a very strong frequency dependence. In the troposphere, the refractive index is a function of three variables: air temperature, air pressure, and the humidity or water vapor content of the air. Atmospheric pressure always decreases with altitude, and both temperature and humidity usually decrease with altitude, so the refractive index of the troposphere generally decreases steadily with increasing altitude. As we'll see in a moment, this change in the refractive index of the troposphere is very important for longer distance VHF signal propagation. As we mentioned earlier, pure line-of-sight propagation at VHF would be limited by the curvature of the Earth. That is, reception beyond the so-called optical or geometric horizon would not be possible. But as we just discussed, the refractive index of the troposphere is larger closer to the ground, so radio waves passing through the troposphere are refracted towards the surface of the Earth. Therefore, this refraction will cause VHF signals to follow the curvature of the Earth, and will extend the radio horizon beyond the optical horizon. Under ideal circumstances, the radio horizon is extended by about 1/3, so you may hear this phenomenon referred to as line of sight plus 1/3. Note, however, that this assumes a standard atmosphere and an unobstructed path, so the actual extension of the radio horizon due to refraction may be significantly smaller under non-ideal, non-standard conditions. The next topic we'll cover is reflections. Like refraction, reflection is a change in radio wave direction at the boundary of two different media with different propagation speeds. Unlike refraction, which involves two air masses, reflection generally occurs between air and a solid object, and this change in direction is more of a sharp angle than a gradual bend. Reflection also tends to be specular, which simply means that the incident and reflected angles are equal. Radio frequency reflection is similar to optical reflection in that reflection is greatest when the reflector is large and smooth or flat compared to its wavelength. A rough surface produces more scattering than reflection, something we'll come back to in a few minutes. Note too that reflection is not lossless. Even the best reflectors absorb some of the incident signal. In VHF propagation, reflections can be either good or bad. Reflections are helpful or good when they permit passive objects to be used as repeaters. And they're bad when they lead to something called multipath. Let's look at each of these cases. At VHF frequencies and higher, it's sometimes possible to advantageously use a large object as a reflector in order to extend range. In this case, signals are bounced over or around an obstacle, here a hill, using a nearby mountain as a reflector. As stated a moment ago, the larger and smoother the reflector, the better the results. Another important consideration when using an object as a reflector is that the reflected signal strength is often best when the reflector is located near one of the stations. Perhaps somewhat counterintuitively, the worst performance is often seen when the reflector is located halfway between the two stations. But reflections can be, and most often are, undesirable. Even where there's a direct line of sight, reflections will create additional paths, usually of different lengths, between transmitter and receiver. This is commonly referred to as multipath. While it's theoretically possible that the signals could be received in phase and add up constructively, this is somewhat rare, and in most cases, multipath reduces signal strength and/or can distort the received signal. Since multipath arises due to reflections, this is a much more serious issue in urban areas due to the large number of reflections from buildings, etc. In addition to impacting received signal quality, multipath also complicates direction finding at VHF frequencies, since it makes it difficult to obtain unambiguous bearings. Multipath can also complicate direction-based services, such as aeronautical navigational aids. For example, multipath caused by reflectors near or on an airport can distort the signals used for runway alignment. Diffraction is different from refraction or reflection in that it causes a change of direction by moving past rather than through or against a boundary. Diffraction most often occurs when a signal encounters a sharp or knife edge on an object. Sharp is more or less a function of the edge dimensions compared to the wavelength. Diffraction allows reception of a signal in the so-called shadow area or shadow zone created by an obstacle, that is, reception in locations where a direct line of sight is not available. Diffracted signals do, however, suffer from diffraction loss or attenuation, and this loss is greater for higher frequency signals. And finally, in rough terrain, it's possible for a signal to be diffracted over multiple objects along its path. The last common VHF propagation mode we'll cover is scattering. Scattering is essentially reflections that occur in many, more or less random directions. Often what determines whether a signal is reflected or scattered is the surface of the object. Rough or irregular surfaces create scattering, rather than the specular reflection we looked at earlier. Scattering is also normally caused by objects with a size on the order of a wavelength or less. The scattering power of an object is very dependent on the wavelength of the signal. Unlike the other common VHF propagation modes we've looked at, scattering from objects at VHF frequencies is usually undesirable. There are, however, some less common forms of scattering that occur with non-solid objects, such as ionoscatter in the ionosphere and troposcatter in the troposphere. We won't be covering ionoscatter or troposcatter in this presentation, but there are several other uncommon propagation modes at VHF, and we'll spend the remainder of this presentation providing a brief introduction to the more important ones. Uncommon here refers to modes that are either uncommon in appearance, that is, they don't occur on a regular or predictable basis, and/or modes that are uncommon in use, that is, that are not widely used today. Despite being uncommon, these modes are important for several reasons. The first of these is that some of these modes can be used reliably for long-distance communications at VHF. As we'll see, they can do this using only natural infrastructure instead of man-made technologies such as satellites, active repeaters, etc. And the viability of these modes was proven many decades ago. Even when these modes cannot be reliably used for communications, they can intermittently and unpredictably lead to signal reception well outside of normal VHF ranges. This can have significant implications for direction finding and signals intelligence applications, especially when attempting to use received signal strength to estimate the proximity of a source. Although there are many uncommon propagation modes at VHF, we'll limit ourselves to the four most important ones: tropospheric ducting, sporadic E, meteor burst, and EME. Let's start by looking at tropospheric ducting. Earlier in this presentation, we discussed how the refractive index of the troposphere normally decreases with altitude. Recall that atmospheric pressure decreases steadily as altitude increases, and air temperature also normally decreases with altitude. That is, higher air layers are colder than lower air layers. However, some weather patterns can cause warmer air to be present over colder air, and this is referred to as a temperature inversion. These inversions can cause large and abrupt changes in the troposphere's refractive index. And these abrupt changes can lead to the formation of something called tropospheric ducts. Tropospheric ducting occurs when signals are refracted back and forth between two boundaries, in a way similar to how signals travel through a waveguide. Signals that are propagated via ducting are often very strong. Ducts are essentially two-dimensional, so signal strength decreases more or less linearly with distance. Contrast this to propagation in 3 dimensions, in which power decreases by the square of the distance. Ducts are capable of carrying VHF and higher frequency signals for very long distances, up to 1,500 kilometers or more in some cases. Ducts also tend to build up and fade away gradually, but once formed, ducts typically persist for at least a couple of hours and may last up to several days. Tropospheric ducting can propagate signals with frequencies from the lower VHF range up to UHF and higher. Similar to the way a waveguide works, the width of the inversion or duct determines the frequencies that can be propagated through the duct. The thinner the inversion layer or duct, the higher the frequency of the signals that it can propagate. It's not uncommon for ducts to become thicker over time, and this increased thickness then allows propagation of lower frequency signals. In other words, a newly formed duct may start by propagating only higher frequency signals, and then later begin propagating lower frequency signals. Tropospheric ducting can often be predicted or forecasted using standard meteorological or weather information. For example, if a region of warm air intersects a region of cooler air and slides above it, this can create a temperature inversion and ducting. Note, however, that stable air masses are needed for the creation of temperature inversions and ducts. If the atmosphere becomes unsettled or well mixed, such as following a storm, then formation of ducts becomes much less likely. And finally, note that ducts will move with the weather. In North America, this movement is primarily west to east. Depending on how they're formed, ducts can be classified as either surface ducts or elevated ducts. These have somewhat different propagation characteristics, so let's take a few minutes to look more closely at these two different kinds of ducts. Surface ducts are created by a single discontinuity in the troposphere's refractive index. This discontinuity forms the top boundary of the duct, and the Earth's surface forms the lower boundary. Generally speaking, surface ducts do not carry signals well over land. The land surface of the Earth is lossy and irregular, and both natural and man-made obstacles will scatter and absorb signals. Surface ducts do, however, propagate signals well over large, calm bodies of water, and these types of surface ducts are often responsible for very long-distance tropospheric propagation at VHF frequencies. Elevated ducts, on the other hand, are created by two discontinuities in the troposphere. The upper discontinuity refracts signals downwards, and the lower discontinuity refracts signals upwards, so signals are propagated between these two discontinuities. Elevated ducts typically form at altitudes of a few hundred meters to several kilometers. Since this is above many surface features, elevated ducts normally are able to propagate signals for longer distances over land compared to surface ducts. Regardless of the type of duct, the best propagation conditions are observed between stations at or near opposite ends of the ducts. In some cases, stations that are along the path of an elevated duct may not be able to launch signals into or receive signals from the duct. Some ducts are, however, leaky and will allow signals to enter or exit the duct at various points along the path. Next, let's look at sporadic E, which, unlike ducting, occurs not in the troposphere, but in the ionosphere. As you may already know, the ionosphere, a layer of charged particles surrounding the Earth, consists of several layers. One of these layers, the F layer, can refract or bend signals at HF frequencies back towards the Earth, enabling very long-distance communications under the proper conditions. This is often called skywave propagation. However, at VHF and higher frequencies, signals reaching the ionosphere are generally not refracted back to Earth and simply pass through it into space. Below the F layer, there is another layer of the ionosphere called the E layer, but under normal circumstances, the E layer is not capable of refracting either HF or VHF signals back towards the Earth. However, under special circumstances, patches or regions of increased ionization in the E layer can refract signals at lower VHF frequencies, enabling limited skywave propagation over longer distances. Sporadic E, sometimes also called E-skip or ES, refers to propagation by means of these highly ionized regions or clouds in the E layer of the ionosphere. This phenomenon takes place at an altitude of approximately 100 kilometers above the Earth's surface, and it can last for minutes or even up to an hour or more. The signals propagated by sporadic E often have low path loss, and therefore lead to high received signal strengths at the receiver. Sporadic E is generally only usable at lower VHF frequencies. Sporadic E can also propagate signals for long distances, typically in the ranges of 700 to 2,500 kilometers. Because of the lower altitude of the E layer, these distances are lower than the distances achievable with F layer propagation of HF signals. This mode of propagation is called sporadic because it's difficult to predict, but it is still common enough to cause problems. For example, European TV broadcasters and American FM radio broadcasters moved up from their original frequencies, in part to avoid issues caused by sporadic E. We can map locations and dimensions of sporadic E clouds by looking at reception reports between pairs of stations. If we draw lines between transmitters and receivers, the intersection of these reports will often show the rough size and center position of the cloud. Sporadic E clouds are, however, not stationary and tend to slowly move over the course of their appearance. In the northern hemisphere, this motion is generally north to northwest and is caused by both winds in the upper atmosphere as well as the Earth's rotation. We've discussed sporadic E in some detail, but have yet to talk about what causes sporadic E. There are, in fact, many different theories about the origins of sporadic E, and as yet there is still no definitive, universally accepted cause. One of the more popular theories is that wind shear or other types of violent weather create thin layers of E-layer ionization. Experiments have shown that sporadic E clouds contain high concentrations of metallic ions. However, the lack of a clear, measurable cause makes sporadic E difficult to predict. It's known that peaks in sporadic E activity occur between May and August in the Northern Hemisphere, with some smaller peaks in December and January. And while there are studies that suggest that sporadic E may somehow be linked to meteor activity or even solar activity, there is still no conclusive correlation between these and the appearance of sporadic E. Although they work in different ways, both tropospheric ducting and sporadic E can produce strong signals over large geographic areas, so it's helpful to understand how to differentiate between them. As we saw earlier, sporadic E clouds can connect many different locations, whereas in ducting, signals usually only propagate between endpoints, or sometimes along the path between them. Sporadic E tends to appear and disappear rather suddenly, but tropospheric ducts normally build up and fade out more slowly, and thus also tend to last longer than sporadic E clouds. Now let's look at meteor burst, sometimes also called meteor scatter, and how meteors can affect propagation at VHF. Meteor burst refers to a form of ionospheric propagation at VHF frequencies. Meteors leave highly ionized trails as they burn up in the Earth's atmosphere, with this increased ionization typically lasting only a few seconds. Meteor heating begins at altitudes of about 120 kilometers, and most meteors are completely burned up before they reach an altitude of 80 kilometers. The ionized trails are cylindrical, usually tens of kilometers long, but maybe only a few meters wide. These trails can be used to reflect VHF signals, bending them back towards Earth, and thus meteor bursts can enable long-distance skywave propagation at lower VHF frequencies. Although not normally visible to human observers, many millions of these meteors enter the Earth's atmosphere every day. Most of these meteors are very small, on the order of less than a millimeter to less than a centimeter in diameter. However, even small meteors are capable of creating ionization. The ionization created by a meteor is a function of both its velocity as well as its mass. Most meteors enter the atmosphere at very high speeds, typically 10 to 100 kilometers per second, and higher speed meteors create higher ionization. We'll come back to this again in a few minutes. Larger meteors burn for longer periods of time, and thus create more intense, longer duration ionization. Meteors can be grouped into two general categories. The first of these are meteors which occur as part of a meteor shower, and the second are so-called sporadic meteors which occur year-round. The way in which meteor trails are used for communications depends in part on the type of meteors that created them. Let's start by looking at shower meteors. Meteor showers are created when the Earth moves through fields of debris. It's generally believed that these debris fields are material left behind by comets. These debris fields travel in known, fixed orbits around the Sun, so the showers that they create occur periodically, that is, on predictable dates during the year. One of the best known and largest meteor showers are the so-called Perseids, which occur every year in August. Most meteor showers usually last for a day or so, and during this time, the number of meteors entering the atmosphere increases by up to an order of magnitude. In fact, the larger showers often create large numbers of trails that are visible to the naked eye. However, since these showers are intermittent, they're less useful for communications. The vast majority of meteors are sporadic. Sporadic means there's no way to predict precisely when or where they appear, and they enter the atmosphere from random locations in the sky. The quantity of sporadic meteors does, however, vary in a somewhat predictable way during the course of a year. Generally, the greatest numbers of sporadic meteors enter during the months of June through August, and the least number enter the Earth's atmosphere during the months of February and March. Time of day, on the other hand, plays a very important role when it comes to sporadic meteors. As the Earth travels around the Sun, it also rotates on its axis. This rotational velocity is added to, or subtracted from, the velocity of meteors that the Earth comes into contact with. In the morning, meteors hit the Earth head-on, and the Earth's rotational velocity is added to the meteor's velocity. In the evening, meteors are catching up from behind, and thus the Earth's rotational velocity is subtracted from the meteor's velocity. This added or subtracted velocity can be up to 30 kilometers per second, which is quite substantial, given that most meteors have velocities of tens of kilometers per second. As mentioned earlier, higher speed means higher ionization, and peak meteor burst ionization therefore occurs in the morning, typically between 4 and 8 a.m. local time. Now that we've covered the basics of meteor burst, let's discuss applications of meteor burst communications. The ionized trails left by meteors only last several seconds on average, and this means that messages conveyed using meteor burst must be short and/or spread out across multiple transmissions. For this reason, most meteor burst communication is used for non-real-time data collection, particularly in areas where cellular or other communications technologies may not be available. An example of this is the U.S. Department of Agriculture's snow telemetry, or SNOWTEL system, which has been in operation since the 1960s. SNOWTEL collects snow and other weather-related data from remote locations across the western United States, and it transmits this data using meteor burst technology. Sites are typically battery and solar powered, and often operate for a year or more without maintenance. The system-wide polling response rate in SNOWTEL is greater than 95%, meaning that meteor bursts can provide reliable communications from locations where other technologies may be unavailable. The achievable distances and usable frequencies are also important considerations for meteor burst communications. Since meteor burst is a form of ionospheric E-layer propagation, the achievable distances are largely a function of the height of the E-layer. Maximum distances for meteor burst can be up to about 2,000 kilometers, but there's also a minimum distance of about 500 kilometers. This skip zone is similar to that seen in HF skywave communications. With regard to frequencies, the ionization created by meteor trails is usable for longer periods of time at lower frequencies. The maximum practical frequency for meteor burst communication is about 150 MHz, with a minimum of around 30 MHz. It should also be noted that ionized meteor trails expand due to the rapid and extreme heating during burnup, and thus signals reflected from meteor trails may experience Doppler shift. The amount of shift is frequency dependent, but can be as high as 2 kHz at the higher end of the frequencies used for meteor burst communications. The last uncommon VHF propagation mode we'll cover is something called EME, which stands for Earth-Moon-Earth propagation. Under normal propagation conditions, natural terrestrial reflectors, such as mountains, can be used to extend the range of signals at VHF and higher frequencies. This same principle can be applied to the Earth's moon, which can, under certain conditions, be used to reflect radio signals and thereby increase maximum communication range. The first experiments into EME, or moon bounce, were started by the United States military in the 1940s, and by the 1950s and 1960s, EME was shown to be viable for use both in radar and in communications. Although EME was never widely adopted for these applications, it was successfully used for many years in SIGINT or signals intelligence applications. For example, the Arecibo dish in Puerto Rico was used during the Cold War to monitor Soviet signals that were unintentionally reflected back to Earth by the moon. Why use the moon as a reflector? The biggest advantage of EME is that it can provide reliable and predictable worldwide coverage at VHF and higher frequencies. This is not possible using any other VHF propagation mode. But as we'll discuss, the ability to use EME is strongly dependent on the position of the moon and the positions of both stations. However, once this condition is satisfied, EME is highly reliable when using proper equipment, in large part because, although the path loss is very high, it is also well known and relatively constant. Another advantage of EME is that it's not dependent on ionospheric or tropospheric propagation conditions, unlike most other HF or VHF modes. This in turn means that EME can be used as a backup or fallback mode if conditions do not support using other propagation modes. There are, however, significant challenges in using EME, and these can be grouped into two categories. The first is the very high path loss, which in turn requires high transmit powers, high gain transmit and receive antennas, and sensitive low noise receivers. The second is that the moon itself is a challenging reflector. The moon is both a small target as well as a moving target, and it also has a very rough and irregular surface. Let's take a closer look at each of these challenges. We'll start with path loss. Path loss is, by far, the greatest challenge when using EME. The two-way path loss between the Earth and its moon is often 250 dB or more, and this path loss increases with increasing frequency. Path loss is a function of many factors, one of which is the distance between the Earth and the moon, which changes due to the moon's elliptical orbit. Path loss can vary by about 2 degrees between apogee, that is, when the moon is farthest away, and perigee, when the moon is closest to Earth. Using high transmit power is the primary method used to overcome this high path loss in EME. In addition to high transmit powers, high gain antennas are another way of overcoming path loss. EME antennas are usually either large parabolic antennas or arrays of antennas. Ideally, antennas used for EME should have circular polarization or switchable polarization in order to deal with losses due to Faraday rotation. We'll come back to this topic later in the presentation. And regardless of antenna type, EME requires antennas that are adjustable in both azimuth and in elevations, since the moon is a moving target that must be tracked as it moves across the sky. The high EME path loss also means that reducing received noise is critically important in EME. Like most other forms of radio communication, noise in EME can be from external sources, in this case either on the Earth or in space, or the noise may be internal, that is, generated from components and devices within the EME system or receiver itself. Since the received signals can be very small, using sensitive receivers and low-noise amplifiers is vital in EME, with noise figure often being the most important figure of merit when building an EME system. Time of day can also play a role in reducing noise, and nighttime operation is sometimes preferred, since this can reduce the amount of both man-made and solar noise. And finally, the position of the moon in the sky can also affect the amount of received noise. Let's take a closer look at why this is. Regarding the position of the moon, clearly it must be above the radio horizon for both stations. Atmospheric refraction, which we looked at earlier in this presentation, does however mean that the moon can be used as a reflector even when it's slightly below the geographic horizon. In fact, in some cases, it can be advantageous to operate EME when the moon is low in the sky, as this can provide ground gain of several dB. But as mentioned a moment ago, the position of the moon in the sky also influences the amount of received noise. Various celestial bodies, such as planets, generate radio frequency noise. Another way of saying this is that at any given time, some parts of the sky are more quiet or more noisy than others. In particular, the sun and the moon should not be close together in the sky when operating EME. Although there are tools for estimating the best operating times for a pair of stations, the declination of the moon can offer some guidance. Declination is the elevation of the moon relative to the equator. The moon moves through a declination range of approximately plus to minus 25 degrees over the course of a month. Generally speaking, the higher the declination, the lower the received noise. Since the moon is also a moving target, both EME stations must track and point their antennas at the moon as it moves across the sky. As seen from the Earth, the moon moves through a 2 to 5 degree arc approximately every 10 minutes, so antennas must be periodically repointed to follow the moon, typically every 5 to 10 minutes. The antenna repointing frequency or interval, that is, how often the antenna must be repositioned, is also partly a function of the antenna beam width. An antenna with a narrower main beam will need to be repointed more often than an antenna with a wider beam width. The relative motion between the moon and the Earth also means that signals reflected from the moon will be shifted in frequency. When the moon is rising or moving towards the observer, received signals will be shifted up in frequency. And when the moon is setting or moving away from the observer, frequencies will be shifted downwards. It's worth noting that most of this relative motion is due to the rotation of the Earth. Like all other Doppler-shifted signals, the amount of shift depends on frequency, with greater Doppler shift occurring for higher frequency signals. The surface of the moon also plays a role in EME communications. As we discussed in the section on reflections, an effective radio frequency reflector should be large and flat, or smooth, where large means large relative to the wavelength of the signals. Although the moon clearly meets the size requirement, it's not a particularly good reflector due to its rough and uneven surface. And as we know from our earlier discussion of scattering, the moon's surface will therefore scatter, rather than reflect, most of the signals reaching it. And therefore, only about 6 to 7% of the signal received by the moon is returned in the direction of the Earth. This situation is made worse by the fact that the moon wobbles slightly, and this loss due to wobbling is called libration fading. As one might expect, libration fading causes fluctuation in received signal power, with variation in loss up to several dB. This in turn sometimes causes choppiness or fluttering in demodulated EME signals. One final topic we need to address is the role of the ionosphere in EME. In HF, and sometimes in VHF, refraction or bending back of signals by the ionosphere is desirable because it can increase the maximum communication range. However, in EME, we need signals to pass through the ionosphere. The appearance of sporadic E, which we looked at earlier, can cause the ionosphere to return VHF signals to Earth, and therefore prevent EME communications. Another potential ionospheric issue is Faraday rotation. Faraday rotation refers to random changes in the polarization of a signal as it passes through the ionosphere. This rotation tends to be inversely related to frequency, and is generally limited to signals under about 1 GHz. Faraday rotation can lead to so-called polarization loss, whereby signal strength is reduced due to a mismatch between the polarization of the transmit and the polarization of the receive antennas. Using circularly polarized antennas, or rotating a linearly polarized antenna, are the two most common ways of reducing the effects of Faraday rotation in EME. Let's summarize these uncommon VHF propagation modes. Neither tropospheric ducting nor sporadic E are sufficiently predictable for use in reliable communications at VHF. Although openings do occur throughout the year, the number of openings between specific geographical endpoints is usually quite small, further reducing the effectiveness of these modes for VHF communications. That said, these modes do create very strong reception outside of normal ranges, so the significance of tropospheric ducting and sporadic E is that they can create interference, sometimes for several hours or even days. Therefore, it's important to be aware of these modes and the possibility of receiving strong signals due to these modes. Meteor burst, as we've seen, can and is being used for reliable non-real-time communication. This is usually accomplished using the sporadic meteors that are constantly entering the Earth's atmosphere, although the appearance of meteor showers may further enhance performance. And while meteor burst does only provide very modest data rates, the station requirements are also very modest, with battery or solar power often being sufficient. And finally, EME, or Earth-Moon-Earth, is capable of providing worldwide coverage at VHF under the proper circumstances. Although EME path loss is quite high, it is predictable and can be addressed using high-power transmitters, high-gain antennas, and low-noise components. One reason to study uncommon VHF propagation modes is that there's been growing interest in alternative or backup modes for communications. For example, the vulnerability of satellites has increased interest in HF for worldwide communications coverage, since HF only requires the natural infrastructure of the ionosphere to accomplish this communication. Uncommon VHF propagation modes, such as meteor burst and EME, also have numerous advantages when it comes to providing an alternative or backup to other forms of communications. First, they require no infrastructure between the stations other than natural features such as the troposphere, ionosphere, or the moon. These are also tested and proven technologies. Both meteor burst and EME were first researched and applied over 50 years ago. They can provide reliable, although somewhat low throughput communications, and under the right conditions can provide coverage at the continent level or even worldwide. And finally, uncommon VHF propagation modes are relatively immune to solar weather, meaning they're not disrupted by events such as solar flares, coronal mass ejections, etc., that can cause blackouts at HF. So in summary, VHF is widely used in broadcasting, in voice and data communications, in avionics, and even for some types of radar. Although many people believe that VHF propagation is mostly line of sight, true line of sight propagation is in fact relatively rare in terrestrial applications. Signals at VHF normally experience refraction, reflection, diffraction, and scattering, with these effects often increasing with distance. In addition to these common propagation modes, there are also several uncommon modes at VHF, that is, uncommon either in appearance and/or in use. The ones we've covered in this presentation are tropospheric ducting, sporadic E, meteor burst, and EME. Although some of these modes are not suitable for reliable communications, others, such as meteor burst and EME, can provide reliable long-distance communication at VHF, and can do so without any additional infrastructure between the stations. This concludes our presentation, Understanding VHF Propagation. If you'd like to learn more about VHF propagation, or antennas and radios used for communications at VHF, please see the links in the video description. Thanks for watching.